Good morning, and thanks for inviting me. I just arrived last night, so I don't know the setup yet of this conference. But what I'd like to do is, for those of you who were here last year, I gave sort of some preliminary results on our molecular gas surveys, and I'm going to give you an update on what we've been doing since last year, and talking about the derivations of molecular gas properties and scaling relations all the way out to redshift 2.5. And I just would like to point out there's lots of people collaborating on this work with me, and some of them I think are here, and well, just want to say thank you. So basically there are two different surveys that I'd like to just include in the results that I'll be presenting. The first is the largest one that we've been doing. It's called FIBS. It's a survey that stands for Plateau de Bure High Redshift Blue Sequence Survey. It's a survey of massive star-forming galaxies lying on the main sequence, the star formation stellar mass main sequence, in two redshift bins. One at redshift 1, where we've selected targets from the Aegis field in the northern sky, and one at redshift 2, where we've mostly selected targets from the various Steidel fields, because our telescope, the Plateau de Bure, is located in the northern hemisphere. So for this work, we've selected galaxies that are in the massive part, the massive quadrant of the main sequence, and the distribution of our sources is given there. And we've been mapping these galaxies in the CO 3-2 line over the past 3 years, and by now have detected in our survey well over 50, and if you combine with what's in the literature, we're now sitting at more than 75 main sequence star-forming galaxies that have been detected in CO. Because of the various intricacies of carbon monoxide to use as a trace of molecular gas, which I don't want to get into too many details for this audience, we are pretty restricted to the most massive tail of the main sequence. And to go to lower masses, there's a second survey that has been led by Dieter Lutz and Amélie Saintonge, and there's a paper that's just in press now, where they've selected 17 gravitationally lensed, cluster lensed main sequence galaxies and mapped CO in 10 of them. And then with using the boost from gravitational lensing, are then able to both go down in stellar mass, so these red points here at redshift 1 and redshift 2, but also go to slightly higher redshift than what we've been able to do with FIBS. So with these two surveys together, plus complementary surveys led by Emanuele Dadi on smaller samples, and various other works in the literature, we're well over 75 and approaching 100 galaxies. And as I'll tell you at the very end, we're now just embarking on a new survey where we'll triple that number in the next couple of years. So I just want to give you the sort of the key results. So the first takeaway point is in mapping CO in these galaxies, we know now that these massive galaxies have high molecular gas fractions. So we're using CO and the various well-known relations that have been established in the local universe with a galactic CO conversion factor to get at molecular gas masses. And this is a function of course, the gas densities, the gas temperatures, and the metallicity. But various indications lead us to believe that a galactic conversion factor is very appropriate for the main sequence populations, even at these redshifts. We also assume an excitation ratio, again, by using some multi-line work that is available in the literature, which leads us to believe that a standard subthermal relation of 3:2 to 1:0.5 is valid in these galaxies. What we're finding is that just for our samples alone, we get average gas fractions of about 50%, but we've now knowing a little bit more, basically from big imaging surveys and applying some assumptions, we can then try to correct our samples, which are biased in both stellar mass and star formation rate, to the incompleteness that we're seeing, which is particularly big at redshift 1, and we can make incompleteness corrections to our gas fractions, and we find then that average gas fractions at redshift 1 after these incompleteness corrections are about 0.33, and at redshift 2 are about 0.5. With the lensing galaxies, we may already be seeing a turnover, and I'll get to that at the end, but it may be that this 0.5 is really a flattening, is really the peak gas fractions that you're going to see at high redshift as population. Now there's an alternative method that you can use to get molecular gas masses, and I would think that maybe David Elbaz is going to talk about this later a little bit, but just for if you're not used to thinking about this, the two methods, one is the using CO as a tracer, the other is using the dust, where you derive first dust masses from SAD fits of photometry from mid to sub-millimeter points, and you assume local dust properties for the dust that you're observing at high redshift. Then you make a dust to gas ratio scaling with metallicity using the local dust to gas with metallicity scalings that have been established by Adam Leroy and collaborators. And then finally, to get back to the gas mass, you then need to know what metallicity you're looking at. And so what typically is done there is you assume mass metallicity holds for the individual sources, get the metallicity, and work backwards to get the gas mass that way. Now there's a lot of assumptions in both methods, and there's lots of discussion as to which method yields the more reliable results. But the takeaway point I'd like for this audience to make is that for the samples that have been done so far, where the two different methods have been used, the two methods actually agree in most of the properties, both in the scaling relations and in the absolute gas masses that are derived. They largely agree, actually. I think for the different communities who are using the two methods, probably surprisingly well. So you'll hear more about the other method from David in a few minutes, or later on this morning. So now let me turn to scaling relations. We know that there are high gas fractions at the high redshift. Now we can start looking at what this high gas fraction, how they depend on other properties of the galaxy. And the first thing that I'm showing you here is that specific star formation rate and molecular gas fractions are very well correlated. So what's plotted here is the gas to stellar mass ratio versus the specific star formation rate for our sample at redshift 1 in black and redshift 2 in red. And you can see there's a very good linear, the blue points are the binned averages. You can see there's a very good correlation, a very strong correlation between specific star formation rate and gas fraction. And in fact, as you go above the main sequence, the thing that's driving that specific star formation rate to go higher is that the gas fraction above the main sequence is also higher. And that's not just seen at high redshift, that's seen at low redshift as well. There's been a complete survey of molecular gas at low redshift led by Guinevere Kaufman and Amélie Saintonge. And this is from their paper, Amélie's paper in 2012, where she's done a similar thing. Here, what she's plotted is variation from a main sequence value for different tracers, and the offset from the star formation rate main sequence. So it's sort of the same thing on the x-axis. And in orange, what you see is the same F gas over M gas over M star as a function of offset from the main sequence. And you can see the same trend using now redshift 0 star-forming galaxies. And So here is where the main sequence at redshift 0 is. Here's what we would call starburst at redshift 0. And here is where things that are almost red and dead lie. And you can see there's a very good correlation. Now, this is what you would just expect if the whole thing were due to gas fractions. But in fact, what Amelie and collaborators find is that there's probably a second effect, which is that you're also increasing the star formation efficiency. But what she's really measuring is that there's a second effect of decreasing gas depletion time also as you go up into the starburst regime. So it's not just the increase in gas fraction, but there's also some correlation with depletion time as you go off the main sequence. So that's the first point, is that molecular gas fractions and specific star formation rates are correlated, and they both go up above the main sequence. The other thing is that molecular gas fractions scale with stellar mass. So we've been able to, at redshift 1 now, we have enough of a sample that we can now look in 3 different mass bins, 5 times 10 to the 10 solar masses, so down closer to 10 to the 10, and then above 10 to the 11th, and then a few by 10 to the 10. And when you, so you see that there's a trend. These are our 3 bin averages at redshift 1, and you see that there is a trend with increasing stellar mass, the gas fractions go down. That trend, if you select redshift 0 galaxies, basically you mass match and star formation you match. So you select the same galaxies on the main sequence at redshift 0 as we've done at redshift 1, you see the same trend here. Those green swatches, what you'd expect from imaging surveys now, just estimating a gas mass from the specific star formation rate. And you can see this is where we need to make our corrections for incompleteness. And so if you do that, you bring these points down there. If you now normalize everything to a fixed stellar mass of 5 times 10 to the 10th solar masses, you see the trend more clearly at all redshifts, basically. At redshift 1 and at 0, you can see a nice clear trend that as you go up in stellar mass, the molecular gas fractions drop. One of the things that one of the main goals for our molecular gas survey was to look at the Kennecott-Schmidt relation at high redshift, because this is clearly, for most observers, most observers do not want to spend all the time to first go getting a molecular gas mass from CO, and they'd like to be able to then, when they have a star formation rate, estimate the molecular gas mass from the Kennecott-Schmidt relation. Now, this has been done a lot in the literature for people observing high redshift galaxies, and the question always is, how valid is it to apply the Kennecott-Schmidt relation, which is a relation between star formation surface density and molecular gas surface density? How valid is it to apply to high redshift galaxies? So what we've now done is taken our high redshift sample and compared it with the low redshift sample. Now, last summer, I think I had already shown you, these are the open points here that are the standard Kennecott galaxies that were already published back in '98. So these are low redshift galaxies. Now applying an updated conversion factor, and we get, so that for the low redshift relation, you get a depletion time, you get a near linear relation with a depletion time of about 1.5 gigayears. We can now do an independent fit to our redshift 1 sample, which is shown in black, these dark black points. And what we're finding, and the redshift 2 sample is in red again, what we're finding is that there is, again, a near linear relation at redshift 1, but the only difference is that there's a slowly varying depletion time. So there's an offset from the redshift relation, which is just due to the fact that our gas consumption time at redshift 1 goes from 1.5 gigayears to basically 700 megayears. But the relationship is almost exactly the same slope as at redshift 0. And so we've confirmed then that you can use the Kennecott-Schmidt relation. It seems to be, at least given the samples we have so far, you can use a standard Kennecott-Schmidt relation for bulk, for at least the bulk properties. For individual points, of course, you'll get some uncertainties, but you can use this relation, and what it shows we're finding as a near linear relation both at redshift 1 and at redshift 0. What that implies then is because our depletion times are so low at both redshift 0 and at redshift 1, is that you need some replenishment of the gas supply, basically, no matter what redshift you look at. Now, what we've been able to do in one case now, this is a paper that's just come out by Reinhardt, where we've been able to now look at a spatially resolved Kennecott-Schmidt relation in one galaxy. So we've been able to take a nice clumpy redshift 1.5 galaxy up at the massive tail and look at it in molecular gas at 0.7 arcsecond resolution. And so what you see here is a molecular gas map in white contours superposed on HST map in green VMAP and a map of the visual extinction. And what you can see is that what you often when you make an optical map, that's not surprising, the CO and the visual map are almost anti-correlated. So there's an offset in the peak of the molecular gas from the peak of the visual, but it's well correlated with the inferred extinction map. Now you can make lots of other the star formation rate map is given here. It correlates very well with the CO, and the extinction here, the stellar mass map here also correlates well with the CO and the extinction. You can see this is one of these nice cases of these clumpy galaxies, and this is something that we certainly would like to follow up with even higher resolution, which we will try to do in the future. The one thing we can also do here, we're very lucky in that this galaxy we can also, we've also been able to map with H-alpha, with the LBT, with the Large Binocular Telescope in Arizona, at about the same spatial resolution as the CO map. And we've been able to, so this is a map of the velocities derived from H-alpha in red and CO in blue. These are the integrated line profiles of H-alpha and CO up here. And you can see they're very, very well correlated. And so we can then use this information to derive a spatially resolved Kennecott-Schmidt relation. And what we're finding is shown here in left. The green points are the individual bins of H-alpha and CO. The black points are the running averages of the H-alpha and CO points. So again, we see a very linear relation also at sort of few kiloparsec scales. So not just integrated over the galaxy, but the relation stays roughly linear also in the spatially resolved map. Now, I think I'm probably running out of time, so you can ask me about the variations in extinction, of course, play a role in this, and I can explain that later during the questions if you would like. So putting this all together, we can now look at the evolution of the specific star formation rate and the molecular gas fractions as a function of redshift. And what we're finding is that if you now use the fact that we see a roughly constant depletion time of 700 megayears, and we see an evolution, a slowly varying evolution of the depletion time with redshift, you can then apply that relation to large imaging surveys, and you get this green relation here. Our FIBS data points are in black, and the averages of individual galaxies from big imaging surveys are in red. And you can see that we're seeing this decrease from high redshift in the accretion epoch down to where this drop between redshift 1 and redshift 0, where the gas fractions are dropping, the specific star formation rates are dropping, and we get down into these more, a star-forming galaxy on the main sequence in the local universe having sort of a Milky Way type star formation rate. So we're now starting to trace this with our molecular gas surveys, and the average here, you can plot it another way. Gas fraction is a function of redshift, and these are the points from the literature here, including our Fib survey. And the galaxy lens work here from Amélie's work shows that this may be now falling off as you go to higher redshift than 2. She's finding an average gas fraction of about 40% at redshift 2.5, and that's consistent with some work from Georgios Magdis, who found for some two Lyman break galaxies also a lower gas fraction at redshift 3. So we may be starting to turn around, and we may start to see a flattening of that relation at higher redshift. So our next step is FIBS 2, where we'll triple the sample size that we have now. And it's a 4-year, 1,000-hour program that's been awarded to us just recently using the upgraded Plateau de Bure, which is now going to be called Noema. They're slowly adding new antennas to double the number of antennas that are on that facility. So within the next 5 years, we'll have 10 antennas and then hopefully 12. So we will more completely probe the both redshift range and also the stellar mass and star formation rate properties. We have a large team that's listed here. We are going to release data products about halfway through. I should say that the first molecular gas properties from the FIBS 1 survey are already available online from IRAM. And we have about 10 new detected galaxies in this intermediate redshift range of 0.5 to 1, which has so far been poorly populated. And we're ready for ALMA, we'll be ready for ALMA follow-up for the targets, at least in the Cosmos field, in about a year from now. So this is just a plot quickly of the coverage that we expect to get in redshift 0.5, 1, and 2, and the different colors just represent the different fields that we'll be probing, including Cosmos and Goods North and Aegis. So with that, I will just leave up my summary and finish.
Okay, thank you. So we have time for a couple questions. John? For galaxies where you have estimates of dynamical masses,
Yeah.
is there any room for anything else other than just molecular hydrogen and stars?
It depends. The uncertainties in both the stellar masses and the gas masses are such that they often, within our uncertainties, they equal the dynamical masses. But that doesn't mean that there can't be a 20% or so contribution from dark matter, right? That's very, very hard to pin down the individual values to better than whatever, 20, 30%. So the answer is yes, there is room.
So you have this strong correlation between the star formation rate and the gas fraction. So I was wondering, things evolve the main sequence of star formation rate, the starburst sort of driven, people interpret it as being driven by emergence.
Yeah.
And I was wondering if that's sort of ethical. Do you expect this high gas fraction just from a random merger?
Well, it depends on the region. So the thing is, you get higher gas fraction within the region of the merger. So we do see this obviously in local ultraluminous galaxies and in some of the submillimeter galaxies where we've been able to spatially resolve. But the difference between those and the main sequence galaxies is that the CO is often much more compact. So it's driven really down into the centers of the galaxies. So for the higher redshift galaxies, it's on a scale of a few kiloparsecs. For the local ones, it's usually less than a kiloparsec. So within the starbursting region, that is true, yeah.
One more question? Yeah, okay.
So when you talk about redshift evolution of the gas fraction, I'm I'm sure you're comparing apples to apples at the same stellar mass?
Yeah. Okay, yes and no. Where we've had control of the samples, so at redshift 2, redshift 1, and redshift 0, we've always selected galaxies with the same properties. So we've tried to match as best we can along the same main sequence.
At redshift 2, you're not sure whether the galaxy is still populated at lower values, right? You showed evolution, but that's at fixed stellar mass. If you look at lower mass stellar mass galaxies, they would probably have lower gas fraction.
They probably have higher gas fraction, yeah.
But there's a spread at these gases, right?
Right,
So
yeah.
it's kind of uncertain what that evolution really means. We might not be looking at the same galaxy, even if it's starting at the same stellar mass.
Right, the galaxies at the same, they evolve into different galaxies. That's, yeah. This is one of the reasons we're doing FIBS 2, is because we want to sample better both above and below the main sequence, but we also want to push down a little bit more in stellar mass at all redshifts. And for me right now, the biggest uncertainty is this redshift range between 1 and 0, because so far what's been published in the literature are only things that are way off main sequence. Basically nobody has really been probing the main sequence during this, where you expect the strongest fall off.
Okay, let's thank Linda again.